proper functional design. So I want you to skip that part. Then once you are done with checking clear spacing and minimum and maximum percentage area provided, you go straight to shear calculations. So that's what I want you to do. All right, let's see here, what do we have? All right, so on Thursday I showed you how to do calculations for monosymmetric columns. They're actually doubly symmetric. Then I asked you to go and do an exercise on the design of or analysis of given sections. Did you do that?
Hello?
Yes, I did.
Okay. And what did you find as the solution?
So I came up with the third row. What was it? It was I don't remember what it was. It was.
Okay, how did you structure, or how did you lay out your calculations? That's important because
Yeah. Okay. So I see it was. So I started off the calculations for. So they gave you the 40. Let me just get it in my book quickly.
Okay, I'm going to share my screen just now. Let's see.
So what exercise was that for, that you were asking?
It was an exercise on steel columns, calculating, analyzing and seeing what would be the best size to use when we were given three section sizes. I think it was a past exam paper on page, let me just fetch my textbook there.
So I came up with, yeah, so
Right, let me just go to that section. You see on page 128, Ryan, I think can you see my screen?
yes, I can see the white screen.
Oh, okay, that's fine. Even now.
Yes.
All right. Ryan posted the picture of what I wanted you guys to do in the section, in that section. Did you get to do that, Mr. Matthew Stubbs?
So I didn't, my WhatsApp thing didn't get messages until yesterday, so I didn't know about it and couldn't see the video. So.
Sure. But do you have videos now?
Well, those videos you did on Wednesday and Thursday, I don't know how to access them.
You just click on that link, that's it.
But it needs someone to accept me to join. So.
No, videos. I made them shareable, so they don't need any extra layer of approval.
Okay, I'll check again, sir.
Yeah, check once more. Right. So the question on 4.1, which reads a steel column supports an axial load of 45 kilonewtons. So you've got a steel column like this, and on top of that column we are applying a load of 45 kilonewtons. The pipe has a length of 4.5 meters So from there to there, that's 4,500 millimeters, and effectively held in position at both ends, restrained against rotation, one end only. Right, so that's the end condition there. Show the necessary calculations and select the most suitable from table A below. Right, so table A is that one which was posted on the group. If you go to your textbooks, it's on page 128, and that table gives you three different sizes: a 48 millimeter, a 60 millimeter, and a 76 millimeter pipe. Right, so this one is a circular hollow section, so it's hollow there. So if you take a section like this, it is circular like this. So you've got one which is having a diameter, the nominal diameter size 48. The actual diameter is actually 48.3. Then you have another one with a diameter of 60.3. Then you have another one with a diameter of what's the diameter? 76.1. 76.1. So we want to find out what is the most optimum solution if you're given these three options. Is it this one, is it this one, or is it that one? So what you are going to be doing, or what you're supposed to do, is to calculate the maximum load carrying capacity, or the resistance which can be provided by each of these sections. Then select something which is greater than 45 but the closest to 45. So you may find out that maybe one section may have a carrying capacity of, let's say, 40. So which means that section is not suitable because it can provide a resistance of 40 kilonewtons, but you want to support 45. So which means that thing will collapse. Then let's say you get this one, and maybe you're getting 47 or 53, whatever the case may be. It's a potential candidate. Then when you select for the final value, maybe you're going to get, maybe it's giving you, let's say, 70 kilonewtons. Whereas 70 kilonewtons is fine, but it's way more than what you require. So you then go and select something which is higher but closest to the applied load. So that's what you do. So yes.
So in this example, I did the steps all the way from the beginning. For the first size, the 48, I worked it all the way from the beginning. What we did on Thursday, I calculated the area and then the ZE and all of that, the radius of gyration. Should I have just taken it from the table for the next two ones, the 60 and the 76? I just used it from the table.
For all, you should have just selected from the table.
Okay.
You did not need to calculate all those things.
Yeah.
Because they were given in the table.
Yeah.
So since they were given in the table, there was no need for you to do those calculations.
Yeah, and it worked out slightly different, the area. So the table had a slightly higher value. I'm guessing that's because it was 48.3 and not 48.
Yes. So, because 48 is a nominal size. It's just a nominal size for assigning a particular size. It doesn't necessarily mean that those are the physical dimensions on the pipe.
Yeah.
Right.
So where is table 17? That's on the question there. Say look at from table 17.
On which question? Which says look at table 17?
Well, on the textbook, page 138, it says on the one row, it says from table 17.
Table Table 17, you use it to calculate the allowable compressive stress, and table 17 is on page it's on page 99 in the textbook. If you go on page 99, you see table 17. Did you find it?
Yes, sir.
Okay, that's fine. So let me show you the structure which you should have used. All right. So you see that structure which we used when we're designing struts. That's what you should have just done. More reduced toolbar. Then you've got your reference section. Reference. Then you've got calculations. Let's say step or procedure. Let's just say procedure here. Procedure. Then you've got your calculations. Calculations. Right. So for your calculations, you were supposed to take the section sizes. So you put column headings for a diameter 48, then you do diameter 60, then you do diameter 76. Right. So those are the different sizes which you were supposed to look at there, right? So what we did when we were designing struts is the same procedure which you'd follow. Let's just go there, but I'm with you just now. You're supposed to determine effective length. LE, right? And what governs calculation of the effective length is clause 8.1.2.1, right? So effective length now depends on the end conditions, right? So if we go to table, let me just go to the table. If we go to table 19, so there is also table 19 there. On page 100, we have to look at the end conditions so that we are able to then calculate the effective length, which is equal to a factor multiplied by the actual length. So this value of K, this factor K, is what we want to determine from table 19, right? So what was the end conditions? Effectively held in position at both ends, restrained against rotation at one end only. Are we there on page 100?
Yes, sir.
Right. So do you see that condition? The second condition, which reads effectively held in position at both ends, restrained against rotation at one end only. And what is the effective length? It is 0.85 multiplied by L. So the value of K there is 0.85. So this is going to be 0.85 multiplied by L. But what is the value of L? The value of L is 4,500. So this is going to be times 4,500. So this is going to be the same for all columns. 0.85, not 0.085, 0.85 times 4,500, 0.85 times 4,500. What answer do we get?
So we get 3825.
3825.
Yeah.
3825. Matthew Stubbs, are you getting 3825?
Yes, sir.
Right. So this is 3,825 millimeters. Right. So once we have determined that, we want to then determine the radius of gyration. So this is coming from the given table, right? So determine radius of gyration. So you need the radius of gyration so that you can later on determine the slenderness ratio, which you then used as the basis for determining the maximum allowable compressive stress. Then from there you are able to determine the resistance which can be offered by that member. So the radius of gyration, in this case, if you go to page 128, that is the small letter r. So if you go to table A, so this one you are getting it from table A, the one which is given in the textbook. So for a 48, the radius of gyration is 16.2 millimeters. R is equal to 16.2 millimeters. Then for a 60 is 20.1 millimeters. Then for a 76 is a 25.4 millimeters. So it's information which you are getting straight from the textbook, and you need not to calculate that from first principles. The other time we calculated it from first principles because it was a non-standard section and we were not given information in a table like this. But if it's information which you can get directly from the red book, or information which you can get directly from a table given, as the case here, you just take that information directly from tables. You need not to waste time and do calculations. So the next part is determine slenderness ratio. So slenderness ratio is equal to effective length over radius of gyration. So this is going to be 3825 divided by 16.2. Here is going to be 3825 divided by 20.1. Then you're going to have 3825 divided by 25.4. Right, what answers do we get for diameter 48 column?
So where is table A? Just on the page number?
It's on page 128.
Thank you, sir.
If you go on page 128, 4.1, you will see table A, which is given there. So the reason why we are making reference to table A is because that's where we are getting our information from there. Right, so what are you getting for diameter 48? Slenderness ratio?
236.111. So you make it 237.
Yeah, 0.111, 237.
Yeah.
Yeah, 236, 237. Okay. You want to round it up? Okay, it's fine. Approximately 237. And for this one, what do you get?
For the 60, it is 190.298.
Approximately 193. Then for the diameter,
One-
76.
It's 190, not 193. So round it up to 191.
Then for the diameter, 76.
It's 150.59, so 151.
151. All right. Just by looking at the slenderness ratio, it tells you that this thing is too small. It has a slenderness ratio which is too high. So my bet is either this one or this one would do.
At the end, none of them seem to work anyway.
Okay, let's see that. Let's proceed with the calculation and see where it takes us. Then from here, what you do is you then say determine you then say determine maximum allowable compressive stress. Determine maximum allowable compressive stress. So it's compressive stress, maximum allowable compressive stress. So where are we getting this? We are now getting it from table 17. So how do you get it? You use these slenderness ratio values to determine the maximum allowable compressive bending stress, which prevents buckling. So if we go to table 17, if I have a slenderness ratio of 237, I go to 230, then I go to column number 9, and column number 9, that coincides with the slenderness ratio of 237. So I see an allowable stress of 17 megapascals. Are you getting the same?
Yes.
17 MPa. Then for a 60, it's 191. So I'm getting a 26
Yes.
megapascals. 26 megapascals. Then for a 151, I am getting a 40 megapascals.
Yeah.
Right, so I'm getting a 40 megapascals. Right. So once I get this, so the next step would be to okay. Copy. All right. So from here, I'm now going to use these values. So let me just erase information, these calculations here. Right, so this time around we are making reference to, we made reference to table 17 already. So now we want to determine the allowable, determine the member resistance, right? So determine member load carrying capacity. Right, so here we are making use of table A once more. Table A. Why we are referring to table A? Because we are going to use the area from there. So the load carrying capacity P will be equal to allowable compressive stress multiplied by area. Right. Remember, a force is equal to stress multiplied by area. So this is the maximum allowable stress, which is PC. PC is equal to these values, PC. Then that PC you then multiply by the cross-sectional area of the section there. All right. So this one, we are going to, I see why Matthew, you were saying none of them seem to work. There might have been an issue in your calculations. And I'm going to demonstrate to you why. So you see the column which is given as A in table A.
Yeah.
That is the cross-sectional area of each section, right? So what do I mean by cross-sectional area? You've been given that. So that shaded region is the area. But the manner in which this area has been given is you are given this as 0.3597 times 10 to the power 3 square millimeters. You get it?
Yeah.
So did you multiply by 10 to the power 3 in your calculations?
Yes,
or you did not?
I did, times 10 to the power of 3.
Yeah, because this is going to be equal to 17 megapascals times, so if you're going to make it square millimeters, then it means you're just moving this thing 3 times to the right. So if I have 10 to the power 6 for 17 megapascals and 10 to the power minus 6 for square millimeters, I can multiply them directly like this. So moving this comma 3 times to the right, it becomes 359.7. What answer do we get? 17 times 359.7. What answer are we getting?
114.9.
114.9. Is it kilonewtons? I want you to express it as kilonewtons, as 10 to the power 3.
Okay. So 6.115.
6.115. Are you getting the same value, Matthew?
Yes, sir.
6.115. So this is 6.115 kilonewtons. Right? So let's do the same. 26 multiplied by the area of the diameter 60 millimeter pipe, which is 624.5. 624.5. What answer do we get in kilonewtons?
$16.237.
16.237 kilonewtons. Then 40 times 1012 1012.2. What do we get?
40.488.
Right, 40.488 kilonewtons. Right. So if you look at all these values, therefore all sections insufficient. Right. So none of these sections is insufficient. Why? Because the ultimate load P, right, is greater than the moment of the load which can be resisted. So we want to carry 45 kilonewtons, and that 45 kilonewtons is greater than that, it is greater than that, it is greater than that. So the conclusion is none of these will be suitable to carry the applied load of 45 kilonewtons, right? So therefore select bigger size section, right? Or use material of higher strength. All right, so you don't need to go and select something bigger, you get it, because it's not provided for in this table. All right, so since you are being asked to select from here, but my suspicion is, you see the fourth row in table A. My suspicion was they wanted to give you another size, but they made a mistake and repeated the same size of 48 there in the last row there. But since it's not given, you make a conclusion based on what you have done, based on your calculations. You get it? You make a conclusion which is based on your calculations, and from our calculations you were right in saying none of them is sufficient if you are using grade 43 steel, and if you are having that kind of arrangement, it means you have to use a bigger section size. You see how much time it took Matthew to solve this thing compared to how much time it took.
Yeah, so it's a lot quicker.
It's a lot quicker. Whenever you are given information, use given information. You get it? Whenever you're given information, use given information. Given information overrides anything else which we might have done in class.
Yeah.
Right. So why am I emphasizing on whenever you're given information, use the given information? It's because at times you may be given certain dimensions, like the overall depth of a beam. Maybe the effective depth is also given. So instead of performing all those calculations which we used to do, you need not to do that. You know what you do? You just use the given information and you state that this information is given. All right?
Yes, sir.
Right. Are there questions around this type of question?
Sir?
Yes.
So why then in the textbook for the answers it says 76 is suitable?
No, because I told you that these guys they smoke some weed. These guys smoke weed, and that's why I told you not to rely on marking guidelines which are in the textbook.
So then what's, why isn't it suitable? Sorry, I just need to get in my head. Why isn't 76 even suitable? What's the number that it should be?
The applied load, the force which is applied, if you were following, we want to support a 45 kilonewton force, right?
Okay, sir.
But this one can carry only a maximum of how much? Of 40.
40.48.
So is that suitable? No, it won't be. It won't be suitable. You get it? So that's why I always emphasize that don't rely on these marking guidelines. In most cases, they have wrong answers. Right? So it's as good as you don't have a set of answers with this thing. It's as good as you don't have a set of answers. So please don't rely on the textbook or on the marking guidelines which are here as possible answers, because they are just not correct.
Thank you, sir.
Right. Now, I gave you the video which I gave you for steel beams. Was it dealing with compound beams, or there was another one which was dealing with selecting a steel beam, a standard steel beam from tables?
So I'm not sure.
Okay, let me see. I just want to check something here, because I gave you, I think, 2 videos on compound beams.
So you gave us the simply supported beams, rectangular section part 1 and 2, and you gave a hot rolled steel beam design example and a hot rolled steel compound beam.
Okay. Let me check this one. Well, on my side, but I was asking Bali if this thing plays. Oh, okay. Watch on YouTube.
Good day all. Welcome to Building and Structural Construction N6, and today we would like to...
Alright.
A factor which is applied to live loads is one.
Right. So you see,
self-weight.
You see this example. Let me just share my screen with you guys. Alright, stop presenting. Present your entire screen. Okay. Alright, so if we come here, right, so you see I've given you an example of how to select or how to design a simply supported beam, and that simply supported beam, you may be given any type of loading scenario, right? So here you're applying what we did in N5, but the main difference is that this time around the self-weight of a beam is included in your calculations. In N5, we never used to include the self-weight of a beam. This time around, you include the self-weight of a beam, and when you do include the self-weight of that beam, you know what we're doing there? We are assuming that the self-weight is 1 kilonewton per meter, right? Which is more than sufficient. So you may be asking yourself, but why do we start by assuming that the self-weight is 1 kilonewton per meter? It is because if you look at your sections, your I sections with parallel flanges, most of them, they don't weigh more than 100 kgs per meter. It's only a few when you get to a 610 by 229, which now weighs about 101 kgs per meter. Most of them, they've got a weight which is less than, which is 100 kilonewtons, 100 kgs per meter. So the fact that most of the I-beams which we use for designing beams have a self-weight which is less than 100 kgs per meter, it makes it reasonable to start by assuming that the self-weight is 100 kgs per meter. Then later on, you will notice that whatever section you select, most likely for the loads which we give you, will have a weight which is less than that. So which means you would have actually slightly over-designed your beam. So it's a valid assumption to say the self-weight of the beam is 1 kilonewton per meter. So let me see. Right, so in this example, I explained the same things which we were doing in N5, and I also explained how to get the maximum bending moments, just like what we did in N5. So it's not a big deal here, right? But the one thing which I want you to make sure that you understand is making use of clauses, making use of the allowable compressive stresses from the appropriate tables, and also making sure that you use the tables correctly, right? So I've explained in detail how you are supposed to come up with that calculation and how you're supposed to verify that a beam is suitable, right? So please go and make sure that you go through this example, because it's also a part where the examiners also want to bring questions from. So that's a section which I want you to make sure that you have an understanding there. All right. So tomorrow when we convene a session, I also want to have a session with you, the last one, tomorrow before your test on Monday. I want to make it a Q&A so that you ask me questions about sections where you feel you're not well prepared. Yes.
I just wanted to ask, we haven't done a concrete reinforced column or pads, and I was wondering if maybe you had a video or two of that.
On ped foundations, yes, I've got a calculation which I can give you on that. On concrete columns, it's straightforward. Concrete columns are not difficult at all. If you go to, that's why you see I wasn't even making a big fuss out of concrete columns. If you go to page, let me show you where that example is. The example on concrete columns. Where is that thing? Let me go to that section on columns. For columns, it's on page. You see, if you go to page 33 of your textbook, if you go to page 33 of your textbook,
yes, sir.
Right, then on page 33 it reads axial load. Those two examples, are examples on how you can design or analyze rectangular or square columns. It's
And
it's
they
just
don't have mistakes.
I know on this one there's no mistakes here. It's fine.
Okay, so these two examples are good.
Yeah, the two examples are okay. It's not a problem.
Okay,
So you can make use of these two examples to do your calculations there.
Thank you, sir.
Yeah, you can make use of these two examples to do your calculations, right?
And for the pads,
For the pad foundations, yes, there's a problem with that example. Please don't use it. The one in your textbook, it's wrong. Don't use that. I will send you a document on pad foundations, and pad foundations are quite extensive. So I'm thinking to myself, should I give you, given that there is you are left with 1 day to the final exam, or should we cross our fingers that is not going to come, because it's quite involving when it comes to pad foundations. Let me just see. Let me just see.
do you know which page it's on so I can cross out the example so I don't copy that?
Right, it's on page. That's the only example on pad foundations. Let me just check the page number for you. It's on page 32 and 33. Page 32 and 33.
Okay.
So
Why does it look like an inverse T? So
yes, because that's how it's analyzed.
yeah.
But the approach which they use in the textbook is incorrect.
Yeah.
For the design of pad foundation. So that's why I'm just looking in my archives here and see which one. Okay, let me do this. I've taught this thing before. Not before, I always teach it every trimester. It's your group, which I haven't taught because of time. Let me go to let me check in my archives here and give you the notes there. Sorry, 81. Right, so save. Let's say columns. Yeah, share. Select all. Share. PDF. I am going to put it here. Let me save it there first. Then I'll put it on your group. 1 2023. Let's just say We are placing it there. It's being saved there. Smart view. Right, so let me look for that stuff. Right, so this one is the section on bed foundations. Right, it's also on beams. It's also on eccentric connections. It's also on it's everything. All right, so I am seeing, yeah, it's also on beams. I've also explained the section on beams. I've also done an example on columns, design of columns. I've done L beams, T beams. So you see this document here, which I have here. I want you to go and look at the section on bed foundations and anything. I'm just going to give you everything. It's the notes which we created when we were doing calculations with the previous group. And here we're designing a bed foundation. It's very, very similar to the design of it is very similar to the design of beams or the design of slabs. Right, so let's say share. I think this is going to be helpful. It's saving. So what I suggest you do is instead of printing everything, just print these sections where we haven't covered. But if you want, you can print. It's a total of 144 pages. But you are much safer with your own notes than trying to copy from someone else's notes, which may not be familiar. So I'm giving you that information here, and you'll be sorted.
Yeah, I think so.
All right.
Yeah, but so it's also in black back screen, so I'm pretty sure that will take up a lot of ink from the printer.
Yeah, it would. So what you can do is you can copy. You can just print the sections which you want, or you can make it negative. You get it? If you make it negative, then it won't take much ink. PDF.
So how do we make it negative if it's in a PDF?
How do you make it negative, by the way? When it comes to print settings, I think there must be a setting where you can play with color settings there. So when you play with the color settings, that's when you can remove that thing.
Okay.
The problem is if I change the background to white right now, then those sections which I've used to write in white, you won't be able to see those.
Yeah.
So with the previous groups, I used to teach them like this, but this thing affects my eyes. That's why you see I use a black background, but even after some time, still that glare which is coming from the screen, even if you have the lowest brightness and everything. That's why I decided to move away from the tablet and go and teach you guys from a camera, from a webcam, because that way at least I'm preserving my eyes. So that's why you see that I've got this information on slides like this, but I haven't shared with you because we were using a different approach. Let's share this, and let's say 1/2023, and let's upload here. Right, so this one may take a bit of time to upload. Let's see. Yeah, I think it's going to. I think it's going to finish just now. Right, so this thing is completed uploading to the portal. Hey, 80 kilobytes. Sort by date modified. So that and that. Let's see if your WhatsApp can handle this. Hope it does. Uh, 42 MB, 70, 83 complete. Let's see if you will be able. Right, it looks like something is coming. Can you try to download that one titled Note 76? Is it the one? This thing which not 76 cancel. Let me just see. It's even there or not 76 here. Or not 76 is this one which we've just done now.
So Note 76 downloaded.
Yeah, N6 T-beams. That's the one with the T-beams and other stuff. So this one is not only T-beams. It's a whole bunch of stuff. This one is not only T-beams, but it's a whole bunch of stuff. Let's see. Yes, I think it uploaded. Then you can download.
I'm downloading it now, sir.
Yeah. Is it opening? Did you manage to open?
So open which one? Open which one?
I'm asking, did you manage to download BSC N6 T-beams?
It's still busy downloading on my side.
Still downloading. Yes?
But it is downloading. It's just taking time.
Oh, okay. Are you saying something, Matthew? Stubs.
No, sir, sorry, my load shedding just went out, sorry. I had to reconnect.
Yeah, so yeah, I think we may for today that's enough information. Tomorrow let's make it a Q&A, so that you guys you've got time to ask certain concepts which you want clarity on. Then I'll be available. So I'll also give you maybe we can do it around same time, maybe between 1 and 2. Then we know we are done with this.
Okay, sir.
Okay, thanks, sir.
All right, thank you. All right, bye.
Bye, sir.
Cheers, sir.
Cheers.
Weekly down with